All right, looking at special cases of refraction. So think about what would happen for the light ray going from a low index of refraction like air into a higher index of refraction like water. What would happen? Well, it will bend. So to draw this, we first draw the normal line perpendicular to the surface, and then we pretend like there's no refraction going straight through. So is it going to bend away or towards the normal line? In this case, it's going to bend towards the normal line. That's your refracted ray, and then there's also a simultaneous reflected ray that obeys the law of reflection. So let's consider this scenario where it goes from a higher index of refraction to a lower, so going from like water to air. So here's our normal line, no refraction. Is it going to bend away or towards the normal line? Well, probably going to bend away from. Okay, and there's also going to be a reflected ray. So the follow-up question is, what would happen if we increased the angle of incidence? So what's going to happen to the angle of refraction? So if we increase the angle of incidence, we're now going further away from the normal line. What's going to happen? So theta 1 is now bigger. Theta 2 is even bigger yet. It's going to bend more away from the normal line. Well, let's continue this pattern. What would happen if we, you also have a reflected ray. What would happen if you increased yet still further the angle of incidence? Then the refracted ray is going to bend more away from the normal line. Well, and then you get the reflected ray. Well, at some point, that angle, the incident angle is going to be large enough that the refracted ray is going to end up going parallel to the surface. And you also have the reflected ray. What happens if you go even further than that? Well, then what happens is none of it gets out, and you have total internal reflection. All of it, all the light is being reflected back into the surface. Okay. So special case here. So the critical angle is the angle which causes, is the incident angle that causes the refracted ray to go parallel to the surface, perpendicular to the normal line. So here we see, here's your critical angle causing your theta 2 to be 90 degrees. So how would you set up Snell's law to calculate the critical angle? So the critical angle would be theta 1, and theta 2, because it's perpendicular to the normal line, is equal to 90 degrees. So we end up with this expression to find the critical angle. So what happens, total internal reflection occurs. So this is when the incident angle is greater than the critical angle, and then none of the light is refracted out of the next medium, but it's all reflected into the original medium. So here, the green is showing the critical angle, the incident angle, showing the refracted ray going parallel to the surface of the water, and some of it's being reflected back in. But then if you exceed that, you go greater than that critical angle, then none of it gets out and all of it is reflected back in. That is total internal reflection. The two requirements for that are the incident angle has to be greater than the critical angle, which we've talked about, and light has to go from a higher index of refraction to a lower index of refraction, because if it doesn't, so here we're going from air to water, it bends towards the normal line. If we increase the incident angle like we did before, it still bends towards the normal line, not as much as not as much as before, but as you increase that, you see how even if you're like skimming the water, you're still bending towards the normal line. So you're never going to get that refracted ray that's going parallel to the surface of the water as we did in the other example going from water to air. So you have to go from a high index of refraction to a low index of refraction to get a total internal reflection. Okay. So another example of a special case of refraction is dispersion. So dispersion is when white light is separated into the color spectrum due to refraction. Okay. We see this when we use a prism sending white light into a prism and it refracts a whole bunch, causing a rainbow to appear. Okay, a whole color spectrum. The cause for that is shorter wavelengths of light actually travel slower through the material than colors with longer wavelengths. So they actually have a slightly the shorter wavelengths actually have a slightly higher index of refraction than the longer wavelengths, therefore causing shorter wavelengths to refract or bend more. So which color has the least angle of deviation, like changes direction the least? It's red. And which one has the greatest? Purple or violet.